Hello, welcome to this sixth, I think, lecture on accessing and transforming data. So in this session, the emphasis is really going to be on how we transform data once we've got it, how we access different types of data. So the motivation for this is really to look at the practical aspects that are associated with how we get hold of data and how we prepare them. So if you think about acquiring data, if you imagine that you're Jacques Cousteau and you decide that you want to make a figure looking at the density, let's say, in the ocean. So you might think, well, I'm going to go and download this data from somewhere. But really, the data center is just this equipment, like we have a series of computers that are all connected here. And so the question in this session is, you're thinking about this nice density figure that you want to make. The computer doesn't really think, it just makes lots of ones and zeros. So the question is, how do we get from one to the other? How do we transfer this data, this series of ones and zeros, into a state where we can make the figure that we want to make? So we're going to talk about various different types, different categories of data. So this question of how we access data and how we process data is really linked also to the history of oceanography and to what data we've collected over time. So, in fact, oceanography is quite a young science, and we haven't had very much data for a very long time. So in contrast to meteorology, on this figure that you can see here on the right-hand side, this is a figure of a weather balloon. So meteorologists, if they want to have information about the atmosphere, it's quite easy for them, in fact, right? They go out, they can go to the place that they want to go to. They take this instrument and they release it, they make their measurements. So for a long time, meteorologists have been collecting this information. Oceanography, it's much more difficult because, in fact, you actually have to go to sea to take the measurement, and it's much more complicated than going somewhere that's on land. And so this difficulty in acquiring data, in fact, meant that until very recently, we didn't have much data at all. So I don't know if you are familiar with kind of the evolution of our knowledge of oceanography. But for example, the first estimates of the heat transport in the Atlantic, which is a really fundamental quantity for our climate, was only made in 1982, so it's 40 years ago. It's not really very long in the whole kind of scheme of things. And so this situation that we find ourselves in now, where we have to learn about how to access data, is really quite recent. So this question of how to deal with large quantities of data. So oceanographic data in the beginning, when people went out to take measurements, this on the top here, you've got a photo from the 1930s. So this was how people used to collect data in the beginning. If you wanted to get a water sample, this guy here with the instrument is Roger Revelle, and you can see he's holding a kind of giant tube that he's taking water from by leaning over the side of the boat. And in fact, if we're collecting water samples now, we still do the same thing, right? But we have a more advanced instrument. So on the right-hand side, you've maybe seen CTDs already. So CTD stands for conductivity temperature depth. And all of these bottles that you can see around this is called a rosette, this yellow thing. So all of these bottles that you can see here around the rosettes are for the same thing that Roger Revelle is doing here in the top photo. So those bottles are going to close, collect water, and come back up to the surface. So this is still the way that we collect water samples. There's also an instrument on the bottom of this float, which is the CTD. So this is the instrument that measures the conductivity, which gives us the salt content, the temperature, and the depth of the instrument. So in fact, this CTD instrument is now used much more widely to sample the ocean than just in this context of collecting data with water bottles at the same time. So in the 1990s, there was a first kind of large measurement program where people decided that, in fact, it was going to be important to measure the ocean and that we should make an effort to do so. So this was the first time that we really started to have more information about the ocean. So up until this point, the information that existed in terms of ocean measurements was really just kind of individual points or individual lines that had been measured in certain places. And in this decade, the WOS decade, excuse me, oceanographers decided that it would be a good idea to make a kind of large scale sampling of the ocean. So over a decade, oceanographers went out and made measurements along all of these lines. And in fact, this was the first time that the ocean had really been sampled at large scale up until this time. So it kind of seems incredible, but this kind of snapshot over one decade was the best view we'd ever had of the ocean up until this time. And it's really only since the the late 1990s and the early 2000s that we've started to have a lot of data about the ocean. So the way that we've had a lot of data in recent years is through what are called Argo floats as a kind of in situ data sampling. So that's these yellow floats, these yellow instruments that you can see here in this picture on the right. And they were in fact originally developed based on an idea by a man called John Swallow. So he invented using kind of bits of material from building equipment, really, the first prototype of these instruments, which are now used very widely in the ocean. So these Argo floats are deployed into the ocean. They float around and take measurements. And there's now 3,000 of them floating freely in the ocean. So a snapshot for the Argo float coverage is that it now looks something like this. So this was taken yesterday. And you can see that there's 3,826 of these floats currently floating around in the ocean, returning data on a regular basis. So this has really drastically improved, excuse me. This has really drastically improved our knowledge of the state of the ocean. So modern floats are now able to survive even in very difficult conditions. So in the polar regions, for example, we can now still have measurements coming back from these regions. And really, with this kind of new massive amount of data, accompanied by satellite data, which is kind of given us a new view of the ocean surface, with numerical ocean models, which have become more and more high resolution, we've had an increasingly large amount of data that we need to deal with in recent decades. And so this has really determined how we access and work with data kind of in the modern era. So the main questions for today's lecture are going to be, firstly, how does data get from somewhere else on the internet to you? So how do you access data? How do you get it from the computer to your local computer? And secondly, what do you need to take into account when you're doing that? So how the data gets from somewhere else to the internet to you is going to depend on a number of factors. So those include the type of data that you're trying to retrieve, where that data is being stored, and also where you want to process it. So this is linked to the kind of aspects of the data, the type of data that it is, and also the size of the data. The format of the data is also going to play a role in that. So if you've got a lot of data, normally that's gridded data. It's normally in a specific binary format. If you're dealing with a time series, that's going to be a smaller data. It might be in a text format. It's also going to depend on how much of the data you want to retrieve. So do you want to retrieve full model output, for example? Are you only working on a small subsetted region? So these are all questions that are going to depend on the physical question that you're trying to answer, and also kind of the computing capabilities that you have available locally. So the plan for the things that we're going to talk about today. We'll start by talking about some kind of generic methods to access data. So we'll talk a bit about web scraping, which is a way to get information generically from a web page. That's not only applicable to oceanography, it can be applied in any context. We'll talk a bit about data wrangling next, which is the process of transforming data into a format in which you can actually use it. We'll then talk a bit about software that's associated with dealing with larger volumes, normally of gridded data. So in that context, we'll talk about ways that we can communicate with standard oceanographic databases. So we'll talk about API and OpenDAP. And we'll finish by talking about cloud computing. So that is kind of moving towards the future of oceanography, potentially. So as we're dealing with larger and larger amounts of data, we need new methods to deal with this data. It's more data than we can process on a local machine. So cloud computing is being used more and more in this context as kind of a future way to treat data. So the context in which you would use these different types of data processing methods, the web scraping and data wrangling aspects you would normally use when you're treating relatively small amounts of data that are potentially unformatted. So you're going to do the work of transforming these data into a format in which you can use them. So you want to produce your figure of density. You're going to need to transform your data that you've collected through this method in order to be able to do that. For using API or OpenDAP, you're working with potentially larger amounts of formatted data that are probably gridded. So it's likely to be satellite data or model output, for example. Normally, you want to download that data from an oceanographic data store. You might not want to download all of it. And normally, again, you're going to be planning to store and analyze that data on either your local machine or a machine at your institute. And cloud computing is something that you would use when you're working with really huge amounts of data. Normally, that's going to be data that's formatted, probably in a gridded form. So again, it's going to be things like satellite data and model output. And we would use this in a context where the data are too large to store or to analyze on your local infrastructure. So the data won't fit on your laptop. It's probably going to be too big. Well, if it's not too big to fit on your local infrastructure, probably other people at your institute won't want you to put it there because it's going to take up so much space. So really, it's for very large amounts of data that become difficult to deal with. Okay, so let's start by talking about small amounts of data. So this is related to web scraping and to data wrangling. So web scraping is the process of extracting information from websites by processing the code of that website. So it's a fairly generic method. And the way that it works is that you need to produce either use a software or to write a program that's going to communicate with the website and extract the data that you want to use. So you produce this software or you use a piece of commercial software to do this. The website's going to return you some data. So normally that's going to be the HTML code and potentially any other files that are stored with that. The program or some of the processing that you're going to do, it's going to transform the data to extract the information that you wanted. And then potentially you're going to do that for a large number of web pages. So you might want to use this method if you're trying to extract a lot of information from web pages. So for example, if you're trying to repeat a downloading process, for example, several times, you might make errors if you do that yourself manually. So you might prefer to write some software to automate that for you. You might want to use it if you're trying to combine data from multiple websites that have different formats and you want to extract certain pieces of information to make a new data set. You might want to use it if you're trying to process or archive data. But overall, the main reason that you would use web scraping is if you don't have another option. So normally for oceanographic data, you do have another option. Normally there's going to be an easier way to access the data. So that would be a good reason not to use web scraping, would be if there's any other way to get hold of the data. And another reason that you might not use web scraping is that sometimes it's not allowed. So in fact, the owner of the website can specify that they don't want you to use this method to access the data on their website. And if they've done that, it's best not to do it because that can lead to you being banned from the website, in fact. So as an example of using web scraping, if we imagine that we're trying to extract the time of tides in some different places. So I don't know if you've ever tried typing some certain pieces of information into Google, and sometimes before it produces the search results, it produces you one of these little summaries of the data. So tide information is a case where it does that. So if I type today's tides in Brest into Google, the thing that it returns at the top is a little summary of the tide information for Brest. So we can see that the high tide today was at 3:53 a.m. and 4:11 p.m. and then we had the two low tides. So I might want to extract that information. So imagine that I want to get tide information for several places. If I change Brest for Gdansk, for example, I get the same format of information. So it's again produced me this summary of the times of the high and the low tides and the heights that were associated. So in fact, we can see that it's produced that information from the same website as for Brest. If I go back, so it was from tideforecast.com, and it's used the same source of information for Gdansk. If we try that for Kiel, we get the same thing. So again, we've got high and low tide, we've got the height, and it's come from the same website. But if I try it for Valletta, we can see that the information's come from a different place. So we've got, again, the high and the low tides, we've got the heights that were associated with it, but the format's not the same as for the information that's come from the other website. So if I wanted to extract all of these different pieces of information and put them together to extract the information about the high tides and the low tides, to do that, I'd need to look at the HTML code of the website, and I'd need to find which piece of information in the HTML corresponds to this information. Once I've done that, I can then identify the part that's kind of corresponding to this information that I want to extract, and I would write software to make use of that. So for example, if I go back to Firefox, for example, here. So here I'm looking at the Google webpage where I've searched for today's tides in Brest. So here we have the information just before the search results. And so this window that you see in the bottom comes from looking at the inspection of the web page. So I do a right click and I look at inspect down here. And that gives me this inspector. And in fact, as I scroll through all of these different parts of the web page on the left-hand side, as I go through these different classes, I can eventually burrow down to find the piece of code that corresponds to this information here. So in fact, if I go further than this, this is the table that contains the information about what the tide time is. So I can see that this has a name. Its name is V3FYCF. It's very instructive. And if I do the same for the letter, so this one that didn't have the same format of information, I can do the same inspection of the web page code. And as I scroll down again, eventually I find that the point at which I get to the information that I want to keep, this table that contains the tide, height, and time, has the same name. It has this V3FYCF name. So by looking at the source code, I learned that if I want to extract this information, that's the part of the web page I'm going to have to pull out and keep and then process later on to get hold of that information about what the tide time looks like. Okay, so one of the reasons that we said we might not use web scraping is if there's a file called robots.txt. So when you use this method, the website owner has to say that it's okay for you to use this method. So some people don't like you to do web scraping, either because they don't want other people to use that information. So they've made it available, but they don't want people to store it. And it could be because, in fact, web scraping can put a lot of demand on the web server. So in fact, it's something that makes a lot of requests. It can put a lot of data transfer demand onto the server. So that can be difficult for the people that host the website. So people sometimes specify whether or not it's okay for you to use this method in a file that's called robots.txt. And it's a list of instructions that says what a website is or is not allowed to do. So in fact, for any domain name, if you add robots.txt at the end, you get this file that tells you about what you can or can't do with that website. So again, it's a good idea to respect the owner's wishes, because if you don't, you might find that they block you from the website. Okay, so web scraping is a generic way to get information from websites. It's widely used, it's flexible, it's relatively efficient, but it's also very difficult to implement, and it makes you do a lot of the work with respect to the transforming of the data. So it can demand a lot of effort to set up. So we saw, to find which piece of information I wanted to keep from Google, I had to go through and find which little bit of the code corresponded to the table that I wanted to keep. I then have to work out how to process that. If Google change their web pages, I need to rewrite that program, because they might change the name of that little bit of code that's storing the information that I want. And in fact, once I've managed to retrieve that data, I have another problem, which is that I also need to work out how to process it once I've got this raw information. So web scraping is a very generic tool. It's potentially a very flexible and useful tool, but if you've got any other option, it's best not to use it. So as a summary, we're thinking about the data that we want to create. We use our web scraping software to get that information from the web page. From that, we get the raw data, but then we still need to get from this stage where we've got the raw data, we need to perform some kind of transform before we can start working with the data and get back to this point where we can make the density figure that we were thinking about. So this missing step is going to be data wrangling, and unfortunately it involves more processing of the data before we can get to this final stage where we can have the figure that we're thinking about. So this term data wrangling is the process of taking our input data and transforming it into a format where we can actually analyze it. So you would definitely need to do this if you've collected the data yourself from a website using web scraping, for example. But sometimes it's something that you also need to do even if you've downloaded your data from an oceanographic data center. So it's something that particularly you have to do if you're working with text files. So gridded data that comes in a binary format is often very easy to work with. It's pre-processed, it comes on a nice regular grid. It's nice and easy to deal with. In contrast, text data can be in any format. And that means that there's potentially lots of different steps that you need to take into account before you can get those numbers into a format where you can use them to perform your analysis. So the kind of things that you might need to deal with can include removing headers or extra text from the data. You potentially need to deal with missing values. You might have to deal with data that's in a certain format within the text file. And potentially you might also need to combine data from multiple sources before you can begin your analysis. So as an example, if you're working with sea level measurements or with bottom pressure recorder data, these are data that come from individual instruments. For long time series, often it's a series of instruments that go one after the other. So this is from the Permanent Service for Mean Sea Level, which is a good source of sea level data. And you can see in this figure on the bottom here on the left, the time series of sea level data at this point, which is in Drake Passage, that's between the tip of South America and the tip of the Antarctic Peninsula. You can see there's multiple colours here. So each one of these colours in this time series is representing a new instrument. So each year they've gone out and changed the instrument at this site, and sometimes there was no instrument there at all. So the bottom pressure recorder looks something like this. It's this instrument that's in the right-hand side here. And here we can see where the measurements are located. So on this website, there's a whole list of files that we can download. So this is the information that we have available. So you can see for each instrument, we've got a start date. So that's when they put the instrument there. We've got an end date. That's when they removed the instrument. And we've got the latitude and longitude. So normally they try to put the instrument back in the same place each time, but with human error, with difficulties of deploying the instrument, that can change a little bit from time to time. So you can see that the latitude remains more or less the same. There's a few little changes, and the longitude, we've got a few little changes as well. So it's going from 0.39 to 0.35, for example. So that's the depth of the instrument. And then we've got a choice to download hourly and daily data. We can have information about the tide, and we can have what's called metadata. So we'll talk a bit more about this metadata in just a second. But let's start by looking at the format of what we're going to download if we try to access this data. So if we download one of these data files, this is the hourly mean data, and we get a text file that looks something like this. So you can see if we want to process this file, before we can make use of these figures that are the information that we actually want to use, we're going to need to deal with all this other information that's in the file. So at the beginning of the text file here, we've got what's called metadata. So this is information that's related to the data, but doesn't actually form part of the data record. So for example, the thing that I might want to plot, if I've downloaded this data, might be how the sea level evolves over time. And the metadata that's associated with that would be things like the latitude and the longitude. So I know where that instrument was located. So that's not something that actually forms part of that data record. It's not a measurement of the sea level, but it's information that's relevant to me potentially, so that I know what I'm looking at. Where was this data collected? We've also got information about who collected the data, and then we've got information about what the columns represent. So this is telling us For example, that there's a flag for bad missing data or an interpolated data in column 2, for example. So we've got this metadata to tell us what we're looking at. If we want to get this data into a format where we're going to process it to read it in using software, for example, probably we need to delete all of this information at the beginning because it's not in the same format as everything that comes afterwards, right? So after this, we've got columns of data that are going to be easy to read into a spreadsheet program or into Python, for example. This before is all kind of free form data. So we need to do something with this. Probably we'll just delete it. To make use of the one column of data, we need to separate that out from the other columns. You can also see that we've got a lot of values that are minus 999.99. So these are missing values in this data set. So we need to decide what we want to do about them. And this was only 1 year's worth of data, right? So we need to do this for every single file if we want to read in the whole data record. That metadata link that we saw before also has another file that's associated with it. So this metadata, again, it's descriptive extra information that's going to tell us about the data quality or about processing that's been performed already, this kind of information. And it tends to include anything that the people who've collected the data think might potentially be useful for you. So things that you might potentially need to know when you're making your analysis. So you can see here there's a note that tells you that they removed a certain offset from the data. So they've done that because they think that corrects the data, but potentially that might be important for you if you find a discrepancy later on, that it's not quite aligned with an earlier record, for example. So this might be important for you. It might not. You might not even keep the metadata, but it potentially contains information that could affect your analysis of the data that you're looking at. So you have a number of options for how to process this kind of data. You can do it by hand. So in that case, you would take this data file, this text file, you would delete this first part of the information. You would then load that into, for example, a spreadsheet program that would be able to separate out these columns that are evenly spaced. And then you would decide which of the information you want to keep, which of the information you don't need to keep. So here, these missing values you might keep or not. You can also do all of these steps semi-automatically using software. So in Python, for example, if you're using the pandas library, that can do a lot of this pre-processing for you. In MATLAB, for example, there are ways to do similar things. So you can skip certain lines of the file when you read in the data. So imagine that we want to combine that with a second file. So on the same website, we've also got information about sea level, for example. So if we look at the sea level in Ushuaia, so this sea level comes from tide gauges. So this is like this instrument that you can see here up on the right. So these have a hole in the bottom. Water comes into that. This is a big kind of tube. Water enters the tube and electronic sensors read the water level to give us a measurement of the sea level height. So we can see on this web page for the sea level, compared to the one that we had before for the bottom pressure recorder, already we've got some different features. So we can see here up at the top of this web page description, we have a warning about the QC flag. So this is the quality control flag. So this is telling us that we should read the documentation. So if we see something like this, we know that we're going to need to look at the metadata for the file. So potentially there's going to be information in there about processing that's been performed on the data. Here, this data is available monthly. So before we had hourly and daily data that were available. Here, the information is only available monthly. Similarly to what we saw before, we've still got some missing data. So before we had holes in the data record, and the same thing has happened again here. So the metadata file for this instrument that we thought we should look at contains quite a lot of information. So here it's telling us about some pre-processing that we should potentially perform if we want the data to be consistent with other instruments. So we can see that they've moved the reference level, so that's the mean height of the sea, for example, at a given time. They've moved that in this instrument. So if we want to combine data from this instrument with a previous instrument that's from before the 1970s, for example, we might need to take that into account. Even if that's not the case, it's still potentially important that we know about this pre-processing that's been performed in case we find discrepancies with our other instruments. So they're telling us here that we should add a certain value to all data values to refer to some certain reference level. So if we look inside the text file that's associated with this instrument, we can see here that we've got a very different format to the previous files that we looked at. So here, there's no information at the beginning of the file now. When we open this text file, all we see is these 3 columns. We've again got missing values, but the missing value here is not the same as the one in the other file. So previously we had -999.99. So this is very common. In fact, the missing value that's used depends on the source of the data. Here it's the same data supplier. So it's not even consistent between multiple files from the same data supplier. So this data file is going to be easier to process for us than the last one because we don't have any extra text at the beginning. But we're going to need to know what these different columns mean. So we guessed that this first one is a date, right? So we've got 1970.3750. But how has that been formatted? It's not very clear, right? So presumably this is a fraction of the year, but we need to know what that represents. This middle column here is got the data. So again, we need to take into account that we haven't got the same missing value. So if we want to combine these different data sources, we need to take into account these differences in how the data is stored. Here, we also need to take into account the fact that this is monthly data and previously we had hourly data, for example. So these are all things that we need to make consistent amongst the data sets before we try to put them together. Okay, so to summarize data wrangling, this is often one of the most boring parts of analysis, right? It involves a lot of kind of deleting parts of the data or trying to put parts of the data into the right format. But if you're dealing either with data that you've collected yourself, or if you're downloading text files from individual instruments, it's something that you might have to do. So you're almost certainly going to need to do some type of this preparation if you've got those type of data. Luckily, if you're not working with this type of data, if you're working with data that's gridded particularly, so that might be satellite observations, reanalysis products or model outputs, which are all kind of common data sources that we would use, they're going to be much easier to deal with. So as soon as your data is on a grid, it's in a fixed format, it comes in a binary file normally, and all of this pre-processing is done for you. So in that case, you might not need to do any data wrangling at all. So if you're working with these gridded data, they're often supplied in this format that's called netcdf. So this format is very good for dealing with gridded data because it allows us to stock multiple variables together. So we can have the longitude, the latitude, this metadata, for example, can be stored with the data that you're going to use. It can deal with data that's on a grid, and it can store metadata in the same file. So you can add comments, free-form comments about the information that's being stored along with that data that you want to analyze. So this NetCDF format is quite standard in oceanography, and in fact, standard software tools are very well equipped to deal with this kind of data format. So if you're working with NetCDF format data, it's quite possible that you might not need to do any of this data transformation at all. But there will be other issues that you need to deal with in terms of downloading and accessing the data potentially if you're dealing with a large volume of data. So this brings us on to the second part, which is how do we get data from a data center? So we're going to be talking about here normally about fairly large amounts of data compared to the cases we've just been talking about. Normally they're pre-formatted in some way. And we're going to be talking about API. So this is technically how the transfer takes place. And we're going to be talking about the OpenDAP and the threads interfaces. So what's an API? So essentially an API is a way for one computer to communicate with another computer. So API stands for Application Programming Interface. When you use a computer normally, so that could be you using Windows or Linux, it could be you using a piece of software, that's a human computer interaction. So it's you interacting with a user interface. So the way that you tell the computer what you want it to do is by this piece of software like Windows that's been designed for you as a human to use it. And the API plays a similar role, but it's for one computer to talk to a different computer. So instead of being an interface for a human to interact with the computer, it's an interface for two computers to talk to one another. So that can either be two pieces of hardware or two pieces of software. So the way that we explain this often is by using the waiter analogy. So if you go to a restaurant and you want to order some food, normally, if it's a normal restaurant, you don't go and interact directly with the chef yourself, right? So you would think about the food that you want. Normally, we don't have this situation where the chef tries to throw you the food from the kitchen. Somebody brings it out to you. So the waiter is kind of the intermediary between you and the chef. You tell the waiter what you want. The waiter goes to the kitchen. He tells the chef what you want. The chef produces the results and he brings you back your food. So we have a situation that looks something like this. So this role, the role of the waiter acting as the person who goes between the person who wants the food and the person who prepares the food, is very similar to the role of an API, allowing two pieces of software or two computer systems to interact. So the waiter's role here is analogous to that of the API. So if you've got a smartphone and you've ever been using Google Maps or a map software, for example, sometimes you might see an alert pop up on your phone, something like this, where it says, can Maps access your location whilst you're using this app? And in fact, when you see something like this, an alert like this pop up on your screen, that's the API, right? So in fact, the Google Maps doesn't know how to find your location on its own. It has to ask the Android system or the OS system how to get your location information. And this is your operating system saying to you, hey, this API is trying to access this information. Is that okay? So this is, in real life, APIs are everywhere, in fact. And we're also using them for obtaining data. So there are many, many different types of API. So you've just seen this one for Google Maps, for example. They also exist for a number of different data purposes. And these certain class that are very useful for us are what's called web API. So these are API that data providers use so that you can tell the computer interface can tell the data store what information you want to retrieve from the data store. So this is potentially very useful because it means you can retrieve subsets of the data, or you can retrieve kind of certain periods of the data. And the web API is then going to tell the data store that that's what you want to return. So you will not interact directly with the web API. This API is between one computer and another one, and you will interact with it via a web page or programmatically. So that could be through Python or through MATLAB, whatever software you use to treat your data. So the way that this works is normally that you have your idea about this figure that you want to make, and you put a request for data that you're going to submit into this data catalog interface. So you'll have an interface like Threads that we're going to look at just shortly that will allow you to select subsets of the data. This data catalog interface then communicates via an API with the data store, and the data store returns this subset of the data that you wanted to look at. That's then passed back to you as this formatted data that you've requested, and from that you can then produce the figure that you've been thinking about. So why do we need this? Essentially, it's because we've got a lot more data in this second category of cases that we're looking at compared to that first web scraping data wrangling category. So ocean climate data are a lot more complicated than generic information, right? They contain multiple dimensions, so we can have latitude, longitude, time, and depth. They're going to be structured normally. So we've got information at a certain number of latitude points, a certain number of longitude points, a certain number of depths. We can potentially still have metadata. Potentially we can have a global scale product. So that's going to involve a lot of data. And potentially the temporal resolution can be high as well. So we might have data every day, for example. So if we've got a product that contains data every quarter of a degree every day, that quickly becomes a lot of data. Also, you might not want to look at the whole globe, for example. So if you're working on the Mediterranean Sea, you're going to be really annoyed if you have to download data for the whole globe and then delete everything except the Mediterranean Sea every time you want to access some data. So you might just want to access an individual sea, you might want to access the Indian Ocean. The data might be available at very high time resolution, but you might not need very high time resolution. So if you only need monthly data, you don't want to have to download hourly data to average that yourself to make that monthly data. And you might only want data at a certain depth level. So if you're only interested in, I don't know, let's say the top 50 meters, if you're looking at upper ocean processes, you don't want to have to download data down to 4,000 meters. So in any of these cases, it's much more efficient for you and for the people who run the data store if you don't have to download the full data set, right? Because that's extra work to extract that data and delete it again afterwards. In any case, normally this kind of data, kind of high resolution, high temporal resolution global data isn't feasible to work with because it's just too much data. So there's a number of different API that exist that are going to let you make choices about what subsets of the data you download. So unfortunately, normally individual data centers have their own individual API. So that means that for whenever you're trying to access data by this method, if your data aren't all coming from the same source, you have to use a different API for each different data center. But the good news is that normally they do give you examples about how to use their API to help you make this request. And the API are generally designed so that it's kind of user-friendly, or that's the idea at least. So you've got some examples here. We're just going to look at two of them. So for ECMWF, so the interface that you will use that will then make use of the API might be a Python program. So you can use their web interface, which will then contact the API, which is uses a thing called Mars. That's their server. And you can see here, this is what they would pass via the web interface for you to retrieve a subset of the data. So this is telling the data store that you want to retrieve data, for example, from, this is the operational stream, so it's not research data, it's recent data. It's at surface level. This parameter is going to be the code that corresponds to the variable that you want to download, so the type of data set, type of data that you want to download. This is the name of the data set. We've got information about the grid resolution that you want. So for ECMWF, you can choose the resolution, the spatial resolution of the data that you want. We can tell it what date range we want and what type of data, the annual data. And they produce also an example that helps you to implement this request if you want to create it yourself using Python. So you would install on your machine their API. So you would need to install that software. And then you can make the request yourself so that your software is going to talk to the API that's going to talk to the data store to bring you back the data that you want. So this can be generated automatically on the ECMWF website. So you can select using the web interface, for example, the data that you want, and then you click on a button and it will help you to generate the script if you don't feel confident doing this yourself to begin with. But this is containing the same information. So this is translated into the Python script that's going to interact with the API afterwards. Through the CMEMS website, I'm just going to go back to my browser for a minute. They also have a method for you to generate the script automatically. So for example, if on the CMEMS website, you're looking at, for example, the global ocean physics reanalysis, or any given data product, you can click on data access, for example. And here, when we want to download this data, so we've got a number of different options. We can download it with daily resolution or monthly resolution, or these are kind of climatologies in variant fields. If we want to download this using the Python API, we can click on the Motu link here. And then here, if I click on API request, it tells me how to make that request using Python. So I've got a number of pieces of information that I'm going to need to fill in. So I'm going to have to tell it where I want to store the data in my output directory here. I'll have to fill that in, the username and the password, but everything else has been filled in automatically for me. So if I want to change the date that I retrieve, for example, I can change these values here for date minimum and date maximum. If I want to change the depth range, I can change that here. If I want to change the variables that I'm retrieving, I can add or remove them here. But until the point at which you feel confident with writing these requests yourself in Python, this can be a really good option to manage making these kind of requests. So the site can generate it for you, and then you just need to submit that request, filling in kind of the basic information to retrieve the information, the specific subset of information that's relevant for you. Okay. So APIs are these intermediaries between two different pieces of software or two different computers, one of which you interact with and the other one is going to be the data store or wherever the data is being held. So these web APIs are quite widely used. You can access them either via a web interface or programmatically through these scripts that you can generate using Python, for example. And the main advantage is that they're going to allow us to select subsets of the data. So that's really important for marine science, because normally the entire data set is going to be huge, and it's going to be much more information than we really need in order to solve our problem. So although different data centers all have different API, the way that we interact with them is often similar, and you should find that they've got guides or tutorials to help you put that into place if you want to use this method to access the data programmatically. So if you want to generate these scripts yourself. The OpenDAP format is a specific type of API. So OpenDAP's been used for a long time, and it's quite widely used in marine science. So it stands for Open Source Project for a Network Data Access Protocol. And it's used on many, many marine data servers. So in fact, although it's a generic data tool, it is kind of perhaps one of its most widely used applications is within marine and atmospheric sciences. And it's really well suited to this kind of data because it works well with structured data. It allows us to retrieve subsets of the data. And also because it's been around for a long time, it interfaces really well with a lot of the tools that people commonly use in oceanography and atmospheric sciences. So IDL, Python, R, MATLAB, any of these software all work well with this OpenDAP method. So the term OpenDAP is kind of has a lot of uses. It refers both to this software framework, and it also refers to kind of the development community that's associated with it. So here we're talking about the framework when we talk about OpenDAP. So I've got another example here. So OpenDAP is the method that we're going to use to retrieve data from one of these OpenDAP servers. And the interface that we're going to interact with is called the threads catalog. So OpenDAP servers normally have the same format of web interface, and this web interface is what's called a threads data server or a threads catalog. So if we look at an example again for the Coriolis server, so where's this one? It's over here, right? So this is from the Ifremer. It's a French institute that distributes some of this Argo data. So here, these threads interfaces, they never look very modern. So they always have this same structure because they've been around for quite a long time. And we start off and we can see the structure of the directory. So this is the main directory, and we've got a number of different subdirectories. So each of these subdirectories, in fact, these are the names of various different institutes that contribute to the Argo program. So these are institutes that pay for Argo floats, that launch Argo floats, or that treat the Argo float data when it comes back. So CSIRO, for example, is the Australian centre that deals with Argo floats, kind of logistics and treatment of the data. So if we click on CSIRO, for example, we get on to another series of directories. So in fact, within this subdirectory, we've got another series of directories, and each of these numbers corresponds to the name of an Argo float. So this 7,900,950 is the name of an Argo float. That's its identifying number. So if I click on this one, I get into the information that comes back from this float. So now I've got the technical and the metadata information about this float. This is its trajectory. And in here, in the profiles subdirectory, I'm going to have a number of different NetCDF files that contain specific information, data that's come back from that float. So if I click now on this one, for example, we get into the Threads data server catalog, and it's telling me the information about this particular profile. So it tells me the size. If I want to download the full thing, it's not very big. It's 112 kilobytes. It tells me about ways I can access it. So either through OpenDAP or using HTTP. And it tells me some more metadata. So I've got the date that it was modified. We've got the salinity, the temperature, and we've got a way to view it down here if we want to as well. So if I use the OpenDAP method so that we can see what that looks like. So again, it doesn't look very modern, but it's the advantage with Threads is that in fact it looks the same in whatever format you, whatever data center you use it on. So contrary to API, the API which can change from one data center to another, this Threads interface always looks the same whenever you see it. So we have a list of the global attributes. So this is the metadata that's associated with this particular data file. And as we go down, we can see all of these different pieces of information that we can download. So in this particular case, because it's an individual measurement that's been taken by the float at one time, none of these pieces of information contain multiple measurements, right? So the number of profiles is going from 0 to 1. So that means we've only got 2 measurements within this file. If this contained a larger number of measurements, I can potentially choose which parts of the data I want to extract using this text box here. So for example, here, I can choose, I've got 2 profiles to choose from. If I want to extract both of them, when I check this box, it fills in automatically so that I'm going to extract both of them. So we're starting at point number 0. We're incrementing by 1 each time, and we're going up to the last profile in the series, which here is number 1. If this was, for example, 180 different values of the longitude, here this would go from 0 in steps of 1 up to 180. So I can choose by modifying this last number. If I just want to keep the last profile, for example, I can put 0 there, and I will only download the first profile, excuse me. Or if I wanted to download just the last one, I can do from 1 up until 1. So in that case, I'm selecting only one profile or the second profile in that list. This number in the middle allows me to choose the jump between the steps that I'm going to extract. So if I've got 180 measurements in the file, if I want to extract every second measurement, so if I've got a resolution of, let's say, 1 degree, and I want to extract every 2 degrees, I can change this second number here, this the 1 that's in the middle here. So if I want to extract only every 2 measurements, it would be 1:2:1, for example. So this lets me select individual parts of the data. If we go down to pressure, for example, so this is all data that's going to be available in the file. I can choose to extract it or not via this interface. So a lot of these are potentially not very useful to me. I might not choose to download all of them, like the data state indicator, for example, I might not be interested in. If we go down to salinity or temperature, for example, so here we are, pressure. So for the pressure, when I click on this one, we've got, again, so the number of profiles is going from 0 up till 1. So this is the 0th profile and the first profile in that file. And then for each of those 2 profiles, there's been a number of measurements taken as the Argo float has moved up or down through the water column. So it's sampling the pressure, the salinity, the temperature as a function of depth. So in this case, we've got 996 measurements that have been made as it's moved up or down through the water column. So in this case, for example, I might choose to keep only, I don't know, every 10th profile, for example. So if I use that format, I'm going to extract every 10th data level as we move up and down through that, through the water column. So I can do that for the pressure, for the salinity, for example, it's going to have the same, the temperature's got the same format, and the salinity is going to have the same format. So once I've done all of that, I've filled in what I want to download from this catalog. I can click on Get ASCII to get the data back in an ASCII format. I can click on Get Binary to get the data back in a binary format. So that's going to be NetCDF normally. And if I'm feeling a bit lost, I can click on Show Help to help me fill in this request form here. So in this example, we've only got quite a limited amount of data because it's just 2 individual floats. But potentially, if we're dealing with a much larger amount of data, this can be really useful for helping us to subset the data that we want to download. The other thing that's really nice with it is that we can also preview the data before we download it. So by clicking Get ASCII, for example, we can download subsets of the longitude or latitude, for example, to check that it corresponds to the thing that we think we're downloading before we commit to downloading a larger quantity of data. Okay, so these, you kind of need to get used to how these interfaces look the first time you deal with them, because it's not necessarily completely intuitive. But once you've got used to them, the format's always the same. So anywhere that you use this threads catalog, you're going to be dealing with the same format. Okay. So this threads catalog is the web interface behind which OpenDAP, this API, is going to talk to the data store. The threads catalogs are just interfaces that are going to allow us to explore this data that we're trying to access. And they're giving us, as we've just seen, both the metadata about the product and also the data itself. So yeah, threads is this catalog. It's the interface to the OpenDAP API, which is again the waiter that's going to talk to the actual data store. If you're wanting to deal with a lot of data, so if you're wanting to download and treat or post-process data, you might want to do it again via Python or MATLAB rather than actually downloading it via a web browser, because that can be quite slow to deal with. So in that case, you might want to kind of use a similar method to the CMWF example, where we write a Python script or a MATLAB program to process that data. You again need to put that information in a specific format to use it with OpenDAP. So you need to formulate the request in such a way that the OpenDAP will understand it. Again, it's something that kind of it's best to look at examples of to understand how that works. So if you look at kind of your favorite data center for the data that you're trying to access, often they have help sections where they explain or give examples of how to actually do that for the specific data that you want to work with. So that can be a good thing to look at in the beginning. Again, when you're trying to get used to how these requests work, it's often nice to start from an example so that you have an idea of what it's meant to look like, because it's not necessarily completely intuitive the first time you use it. Okay, so OpenDAP API is this protocol for accessing data. It's been widely used for many years, and it's well suited for marine data because we can select only subsets of the data rather than having to deal with very large amounts of data. And it also allows us to potentially look at the metadata or to preview the data before we download it. The threads catalog is this interface that's going to help us to navigate the data via a website. So you can use a web browser to do that, but also once you become comfortable with kind of how the requests work. You can also potentially do that by using your favorite data software as well, to make that an automated process if you're dealing with a lot of data. Okay, so that brings us on to the last part, which is what happens when we've got very large amounts of data. So we're going to be talking a little bit about supercomputers, but particularly about cloud computing, just to finish. So cloud computing is a term that we hear quite a lot now in general life. And in fact, the essential idea behind it is that you're going to be running a program or accessing data in such a way that to you, it seems like it's all happening on your computer. And in reality, it's all happening elsewhere. So normally it's a very, the idea is that it's very easy and transparent so that it seems to you like you're not dealing with a lot of data. Whereas in fact, often there's massive amounts of data and computation that are involved in these kinds of calculations. So the current state of affairs is that this is largely still something that's being implemented by private companies. So the kind of big companies that host this are Google and Amazon. They have massive amounts of servers that are capable of treating these large amounts of data. They have all this infrastructure, and people hire space on these machines. So the reason that this has become widespread in science, or widespread, it's become increasingly popular in science, is the same reason that it's become increasingly popular in everyday life. And it's the reason also that it's Google and Amazon that run these servers. It's because they're companies that are dealing with massive amounts of data. So they're big enough companies for it to be worthwhile them investing in this infrastructure. And then for most other people, so for kind of small to medium scale companies that have to deal with large amounts of data, the expense that would be involved in setting up this kind of infrastructure is too much for them. So it's more economically viable to outsource that work to somebody else. So they pay Google or Amazon to take care of putting in place the infrastructure, supplying the space on that machine, supplying the computers to perform these calculations. And then the smaller and medium companies don't have to take care of these technical aspects. And in science, it's the same issue. So we were talking a bit in the beginning about the different types of oceanographic data. So we've gone from this case where one man leans over the side of a boat with a bottle to the case where we now have thousands of floats in the ocean, where we have satellites with high data resolution. And we have much more data than we had before, and we need to work out how to deal with it. So new data sets that we have now have the same basic requirements that aren't fulfilled by kind of traditional computer infrastructure. So we are kind of at an individual institute level often don't have the resources to store such massive amounts of data. So these many new data sets all require much different scales of storage and of capabilities in terms of storage and processing. So new instruments are providing higher and higher resolution data, and numerical models as well are being run at higher and higher resolution. So in terms of data size, it used to be common for computer numerical simulations to produce several gigabytes of data. And now it's quite common to produce several petabytes of data. So it's not at all the same size of problem. And so not only for the storage of these data, but also for the analysis, that means that we need new solutions. So this is a figure taken, it's a still taken from a simulation that was performed by Ocean Next, and it's at a 1/60th of a degree. So that corresponds to a resolution of about 1 kilometer in the Mediterranean, for example, here. So you can see the detail that gives. We see all of these eddies swirling around in the ocean. We can see lots of tiny features in the ocean state. And if we compare that with a grid from before, So this is a 1 degree grid configuration, for example. You can see that the grid on the Mediterranean, in that case, it will correspond to, I don't know, a couple of tens of squares by a couple of tens of squares. So we're not going to see at all the same kind of resolution between those two grids if we compare the two. So here's the comparison of the same two regions. So in a 1 degree configuration, the Mediterranean Sea is 16 points by 42 points. And in a 1/60th of a degree configuration, we've got 960 points by 2,520 points. So for each individual time step, it's a wealth of new information scientifically, but also it's a whole new world of to deal with in terms of data storage and processing as well. And this evolution has happened over a period of let's say maybe 25 years, right? This increase in kind of resolution. And this is true not just for ocean models, but also for satellite data. So the first satellite altimeter was launched in 1992. That returned data, it's still returning data with a spatial resolution of 0.25 degrees. So that corresponds at the equator, the largest point, to about 28 kilometers. And this next generation instrument that you see down here is called SWOT. It was launched last year, and that's now measuring the sea surface height with a spatial resolution of 1 kilometer. So again, that's order 28 squared times more data for an individual 1 degree square, right? So as scientists, we want this new data, right? Because this new data, these new higher resolutions exist because people think that we need this data to answer existing problems, existing questions that we have about the state of the ocean. So a common one is the energy budget, the question of where the energy that drives the ocean comes from, where it goes, and how it gets transferred between different sized flow features. So how does it get transferred between large scale currents and very small scale eddies? So to answer that question, we need high resolution data. But in fact, we've now starting to have this high resolution data, and we need to find ways to work with it. So there are several kind of problems or difficulties about this new type of data. The one is just in terms of sheer quantity, it's much more than we're used to dealing with. In terms of analysis, the software that we would historically use is not necessarily well adapted because it's not used to processing such large amounts of data, right? That requires more memory on your computer. It might require you to split the data into smaller pieces so that it doesn't take so long to process. And often our local infrastructure might not be powerful enough to deal with kind of massive amounts of data like this. So how can we work with this big data? So the new model resolution, the new high resolution model simulations are still produced on supercomputers, which is the same way that we've produced numerical simulations always. So these look like, this is taken from the film The Martian. I don't know if you know this film. So this guy comes and he sits in with the supercomputer to perform his calculation, which is something that would never happen in real life. But this is what a supercomputer looks like. So we have all of these arrays of hardware that are kind of put together in a big room. So these computers you would connect to remotely. Normally you would connect via an interface. You would run your model simulation on these machines, and then you would either transfer the data to your local server to analyze, or you might run the simulation on your supercomputer at your kind of local institute. Right, so the Spanish supercomputer, for example, looks like this. So we've got this is the Barcelona Supercomputing Center supercomputer. This is one of the largest supercomputers in Europe at the moment. So you can see the size, right? It's about the size of this chapel. And it's just lots of rows of data servers, basically. So these are lots of different rows of data storage and computing modules that are all put together that are kind of connected to allow large simulations to be run. And from the side, that looks something like this. So with these new simulations, essentially we now have two options. When we've got these massive amounts of data, we've got either the option that we leave the model simulation in place on the supercomputer, and that we also use the supercomputer to perform this analysis of the data. So we consider that the data is too big to move to our local infrastructure, and so we perform the analysis there. Or we might use cloud resources. So this is what's happened in the recent CMIP6 experiment, for example. So this is the coupled model intercomparison project. It's a large community effort where people produce lots of different simulations simulating future climate change, and that often influences the IPCC reports, for example. So in that case, those resources are also available in the cloud since the last round of that project. So the other thing that's changed with respect to these new amounts of data is that people have also started increasingly to use data science techniques. So now that we have such huge amounts of data, the real kind of increase in machine learning and this kind of these newer methods of data analysis that have really become popular over recent years is that they use or require massive amounts of data. And because we're now starting to have that in oceanography, this has kind of also prompted an increasing interest in the application of these techniques to marine science data. So for people who use these kind of techniques, that often requires uses of a GPU. It's a graphics processing unit rather than a CPU, so computer processing unit. And historically, we haven't had access to those kinds of resources. So normally we've worked on the supercomputing infrastructure, which historically has been made up just of CPU processors. Some supercomputing centers now do offer GPU processors, but often people are also using other resources such as the cloud to have access to those kind of data now. So it seems likely that we're going to need new ways to work with marine data going forward, but that's not a new phenomenon. So at the time when we moved from 1 degree to 1/4 of a degree model resolution, that seemed like a lot of data at the time, right? So we increased by kind of factor 4 squared each time, right? But kind of it's to say that scientists have always had to adapt. So technology has always been evolving as people have kind of produced these different types of simulations. However, it does seem unlikely that we're going to continue with a model where all of our data, at least, is stored on the local infrastructure. So this is a graphic that's showing you the annual size of so they call it the global data sphere. This is all of the data that exists in the world. And it's predicted just to keep increasing exponentially. So if we've got the size of the data prefix, so it's a zettabyte, so that's 10 to the factor 21. So we're talking about 10 to the 12 gigabytes of data. So that's 175 of those predicted for the year 2025. So there's more and more data as time goes on. It seems likely that we might as a community move to a state where we don't do analysis on our local machines anymore for these kinds of data. That's the example of the CMIP6 data. Okay, so to summarize, we've seen kind of 3 different categories of data that we might want to deal with. We started with these kind of small amounts, well, relatively small amounts of unformatted data, which we might have to clean up and transform ourselves. So that's going to be the most effort required if you're dealing with these text files. Gridded data, if you're accessing moderate amounts of data, you're probably going to be doing that through a dedicated interface and probably bringing that back either to your local machine or to your local server. And the least effort required by the user is going to be if you're dealing with cloud computing. So if you're dealing with very massive amounts of data, they're normally going to be in one of these pre-gridded formats, and you're going to be using that potentially remotely on somebody else's machine. If you're dealing with small amounts of data, it's feasible that you can do the processing for these massive amounts of data. Everything has to be automated, right? So that's even going to be the case if you're dealing with open dApp. You're going to need to have a system in place so that you'll have a management system for the data that you're retrieving, so that that's done automatically. So the number of these different data access models are going to depend on your use case. So it's going to depend on the size of the data, the type of the data, what you want to do with it, and where you want to process it. And we've seen to finish that probably this increasing data volume in the future is potentially going to mean that we have to work with data in new ways. So that might involve heavier reliance on cloud-based systems. It's not clear at the moment. So that's an evolving technology, but this has kind of happened before and it's probably going to continue to happen again. Okay, so I'll stop there. If you've got any questions, don't hesitate.